Statistics. These are the notes for 11.2. We're looking at what's called a goodness of fit test. These are still hypothesis tests, so we're still going to be determining if there's enough evidence to reject the null or fail to reject the null. What a goodness of fit test does is we basically look at some sort of observed data, some observed frequencies, how often stuff is happening, and we're going to compare that to some sort of claim. If the observed data is close to what was claimed, we would say it has a good fit. That's why it's called a goodness of fit test. Now, here's the thing, data is never perfectly going to fit what we're expecting. But let's say, for example, I did some sort of study where I wanted to know the frequencies of landing on a die, for example. So we've got, a single die, and we want to know, okay, how often is it landing with each one face up? So let's say I had the outcome, how many times it happens, that would be my frequency. And my outcomes, obviously, on a standard die are 1, 2, 3, 4, 5, 6. And let's say I roll the die a whole bunch of times and I get, actually, sorry, they should be the observed. I'm going to put an O there for observed frequencies. Let's say it lands 18 times on 1, 22 times on 2, 16 times on 3, 20 times on 4, 21 on 5, 19 times on 6. Now, we would expect the outcomes to pretty much be equal. We're assuming that it's a fair die. We would expect the outcomes to be equal, which on this problem would actually be, and I'll explain how to do this in a sec, it would be 19.3 each time. That would be the expected number it landed on each one. And again, I'll explain a little later in the notes how I arrived at this number. Now, here's the thing. The observed and the expected are not going to be exactly the same. It's real world data. It's not going to come out perfect. And obviously, since it's 19.3, that can't happen anyway. It's got that decimal. But the question is, are the observed and expecteds close enough to where the observed matches what was expected? Is it close enough or is it not? Does the data fit or is it too far apart? And again, how far is too far? That's where we'll have to apply some statistical methods here. So we have our observed, we have our expecteds. In this, we have a K number. That's the number of categories, which in this problem, K would be 6. N would be the total number of trials, which is, if I were to add up all of these, if I summed all those up, they added up, by the way, on this fake problem to 116. So that would be my N. So we have that new K value, which is how many different categories I have. Now, the nice thing is that the hypotheses on these are always the same. Oops, that's not what I wanted. I wanted to create a new one. There we go. Basically, the null hypothesis is always that there's an agreement with the claimed distribution. The alternative is that they don't agree. So basically, we're testing against, do they agree? Now, the claimed distribution can be anything I want it to be. But for our purposes, the claimed distribution is always going to be equal frequency, at least on like tests and stuff. The Q, equal frequency. Now, this does involve a new test statistic. So if you remember, we've had Z test statistics and we've had T so far. This introduces a new one called chi-square. It's not chai, not the drink, It's chi square. And chi is a Greek letter. Chi looks like a little X that's blowing in the wind a little bit. Kind of a little X that's blowing in the wind. And it's called chi square. I'm not going to get into specifics. It's pretty high level stuff of why it's called chi square. But at no point do you have to like take the square root and get chi by itself. It's just called chi square. And if you actually look at the very back of your green packet, you have a chi square table. And we'll get to that in a little while as well. So we have a formula for chi square. It's basically take every observed minus the expected. That's going to tell us, when I do the observed minus expected, that's going to tell us how far away what we observed was from what we expected it to be. So on that other example, you know, if I had 18 for my observed and 19.3 was expected, I'm a distance of 1.3 away. But I have to be careful. This is something we dealt with way back in the beginning of the semester. I don't like having negatives. So the way we got around that in statistics was we squared it. That got rid of the negatives. We divide by the expected. The reason we do that is that's going to give us a feel for how many times over is this observed from what we expected. It gives us kind of a what I would call a score of how crazy is the observed versus the expected. If the observed was really close, this is going to be a very small number. If I did this divided by 19.3, that's going to be a pretty small number. But if I had 82 up here, this is going to be a massive number, and it's going to make it, oh wait, my observed was way off. The last thing we do is we're going to do that for every category and then add them together. And again, we'll see through problems what the heck I'm talking about here. P-values, we cannot find by hand. We have to use StatCrunch to get exact p-values, and I will show you how to do that as well in these notes. We will be focusing, though, also on critical values again, which we did a little bit back in chapter 8. We're going to use degrees of freedom. The degrees of freedom are based off of the number of categories. So that's that K. So on that first problem, we had 6 categories. So the degrees of freedom would have been 5. Now, this chi-square thing, there is a link to a short video if you want to watch it. The chi-square is always right-tailed, just to give you a feel for it. Whereas our Z-curve was bell-shaped and our T-curve was also bell-shaped. Remember, the T-curve could change based off of the number. The chi-square is not bell-shaped. It is a highly right-skewed graph. So this is what the chi-square graphs in general look like. This is Z and this is T. Now, another thing, just like with T, based off of the size, the sample size, T could change. Same thing with chi-square. But in general, chi-square has this curvature. And we're always going to be looking at the right tail. We don't have to worry about left tail, right tail, or two tail. It's always that weird stuff is over on the right side. Always, always, always. Oops. So in general, what are we doing with the goodness fit test? If we have a close agreement between the observed and expected, if basically the observed data values are close to what we thought was going to happen, that's going to give me a small chi-square value. So there's going to be basically a little curve that we're going to look at, X and Y. And if they're close, then we're going to get a chi-square value that's pretty low. By the way, the chi-squares don't have negatives. It goes from 0 out. If there's a large disagreement, then that chi-square value is going to be way over here somewhere. Remember, off in the tails are where the weird things happen. So if we get something way off in the tails, we're talking about something that's weird. Weird means reject. Remember that weird always means reject. So if it's significantly large, we'll reject. So basically, here's what we're going to do. We're going to do a bunch of calculation to figure out the chi-square value. We're going to compare that chi-square value to a critical value. And the question is going to be, if the chi-square value is beyond the critical value, we're going to reject. If it's inside of the critical value, or on the left side of it, that's not weird stuff, we're going to fail to reject. And again, this is a lot of theory right now. We'll get to some hard examples in just a little bit. So this kind of summarizes what I just talked about. If we have a small chi-square value, then that means we will fail to reject the null. And that leads to the assumption that this was a good fit. If the chi-square value is big, it's going to be out in the tail. That's going to result in a rejection of the null. And we're going to say it's not a good fit. What I observed does not fit what I expected. And we will be using this same table, flowchart thing, that we've been doing for the past 3 or 4 weeks now. So for number 1, we have records of randomly selected births based off of the day of the week they happened. So again, I have observed values here for each day of the week at some hospital. Now the claim is that, hey, babies don't know about our difference between weekdays and weekends. So it would make sense that it should be an equal frequency, the number of babies born on each day of the week. Now, obviously, they're not the same, but we're going to measure this. So my null is that the births occur with the same frequency. Oops. There we go. Same frequency on different days. The alternative of the same frequency is that at least one day is different. So my original claim, same frequency. The alternative to that is one of them is at least different. So how do we do this? The first thing I got to do is figure out what my expected value would be. So if I'm expecting it to be the same number of births per day, I need to figure out what my total sample size is, which if I add all these together, that gives me 777 births. If I think it's going to happen with equal frequency, the same number of births per day, 777 divided by 7 days gives me an expected of 111 days, or excuse me, 111 births per day. Now, obviously, my numbers aren't the exact same as that, but we need to figure out how far apart they are. So in the next column, I do observed minus expected. And I get all of these numbers. Which again, this is saying how far apart is my data from what was expected. Now, obviously on Monday, it happened to land perfectly, so it wasn't any far apart, but it definitely was far apart on other days, especially obviously Sunday was pretty far apart. I don't like having negatives, so I square each value, and that's going to lead to these numbers. I'm squaring each one of the red numbers. And for the next step, I divide every one of those blue numbers by the expected, which the expected every time for this is 111. I'm going to carry these out to 3 decimals each. So the first one will be 1156 divided by 111. And that's going to give me 10.414. The second one's 0. Next one is 196 divided by 111. And again, I'm going to round these to 3 decimals. And as I keep dividing, I do get some repeats here. So again, that was each one of the blue numbers divided by 111. I'm actually almost done with finding my chi-square value, which is my test statistic. My next step is to take each one of these green numbers and add them together. So I'm going to sum those together. And if I add those together, I get 17.441. That is my chi-square value. That's my test statistic for this problem. So we've done all the legwork. On the next video, we're going to figure out how to actually make a conclusion.